Are seed oils bad for you? Hi, I'm Derek. I'm a preventive cardiologist, and as a preventive physician that's also active on social media, I'm exposed to a lot of the same information and misinformation that my patients are exposed to. And an active topic of conversation has been concern about seed oils. Concern that seed oils cause inflammation, oxidize and damage your cells, are created in a harmful industrial way, and even that they are the real cause of obesity. Sounds scary. So, are seed oils bad for you? Are they harmful? Are they harmless? Are alternatives like animal fats better or worse for your heart health? What I will do in this video is address some of the main concerns I've seen about seed oils in an evidence-based way, not with clickbait, fear-mongering opinion that's meant to capture your attention, but what's reality? Let's go together directly to the studies and see what concern is supported and what's not. Part 1. What are seed oils? Okay, first, what are seed oils? Well, and I promise you this will be more interesting than it sounds. What are oils? When people talk about oil in nutrition, what they're really talking about is dietary fat, really fats that are liquid at room temperature. From a chemical standpoint, nearly all dietary fats and oils are triglycerides. That means they're made of one glycerol backbone with 3 fatty acid chains attached. Then it's those fatty acid chains that determine how a fat behaves in the body, whether it's solid or liquid, how it affects cholesterol, and how it's metabolized. So then the distinction between a fat and an oil is mostly physical. Butter would be a solid at room temperature, olive oil is liquid, but chemically they're built on the same structure. The difference, the important difference, comes from the types of fatty acids attached to that backbone. We can classify them into different categories based off their structure. The first major classification is saturated versus unsaturated fat. Saturated fats contain no double bonds in their carbon chain. Every carbon is fully saturated with hydrogen, which makes the chain straight and allows the molecules to pack tightly together. That tight packing is why saturated fats are usually solid at room temperature. Common sources include butter, lard, coconut oil, and animal fats from meat and dairy. When eaten in excess, saturated fats will tend to raise LDL cholesterol, and we know that LDL cholesterol is causal in coronary artery plaque. Unsaturated fats then, in contrast, contain one or more double bonds, so they are not saturated with hydrogen. Those double bonds introduce bends in the fatty acid chain, preventing the molecules from being tightly packed down and making these fats liquid at room temperature. Unsaturated fats are generally associated with a lowering in LDL cholesterol levels when they replace saturated fats in the diet. So that's saturated and unsaturated fats. Unsaturated fats, and I promise this is important, can be divided into monounsaturated and polyunsaturated fats. Monounsaturated fats have a single double bond. A classic example is oleic acid, which is abundant in olive oil and avocado oil. These fats are relatively chemically stable and have consistently favorable effects on lipid profiles when they replace saturated fat. That's a key point from this video. Saturated fats raise LDL. Unsaturated fats are not associated with raising LDL, and a classic monounsaturated fat is oleic acid in olive oil and avocado oil. It has a favorable impact on LDL. The other kind of unsaturated fat, polyunsaturated fats, have poly or multiple double bonds, 2 or more. Because of this structure, they're more flexible in cell membranes and more biologically active. Polyunsaturated fats include the omega fatty acids. These omega fatty acids play important structural and signaling roles in human physiology. They're found in seeds, seed oils, nuts, and fatty fish. The term omega refers to where the first double bond appears when counting from the methyl or omega end of the fatty acid chain. This numbering system matters because humans cannot convert one omega family into another. Omega-3 and omega-6 fats are metabolically distinct, and both must be obtained from the diet. Omega-3 fatty acids include alpha-linolenic acid from plant sources and EPA and DHA from marine sources like fish. These fats are incorporated into cell membranes. They influence inflammatory signaling pathways, and they can have a modest lowering effect on triglyceride levels. Many Western diets are relatively low in omega-3 intake, which is why increasing omega-3 consumption is commonly recommended. Omega-6 fatty acids are also essential. The primary omega-6 fat in the diet is linoleic acid. Omega-6 fats are major components of cell membranes and serve as precursors for signaling molecules involved in normal immune and vascular function. They're abundant in seed oils, as well as nuts and seeds. So now, there is a common misconception that omega-6 fats are inherently inflammatory. That comes from a lack of understanding about how these pathways work. There are omega-6 derived molecules that participate in inflammatory signaling, but in the human body, in controlled human trials, studies consistently show that typical dietary intake of linoleic acid does not increase systemic inflammation. So if we understand the biochemistry and the physiology, the presence of omega-6 fats in the diet is normal, it's required, and it does not increase systemic inflammation in humans. Omega-3 and omega-6 fats do share some metabolic pathways though, and they compete for the same enzymes. Because of that, the conversation is often framed as an excess of omega-6. A more accurate framing is that omega-3 intake is often too low. It's not that omega-6 is too high, it's that the diet is deficient in or too low in omega-3. Clinical trials show benefit from increasing omega-3 consumption, not from eliminating omega-6 fats. So applying this to fats in the diet, when you step back and look at dietary oils as a whole, their health effects depend on what types of fatty acids they contain and what they're replacing in the diet. Oils higher in unsaturated fats, both monounsaturated and polyunsaturated, lower LDL cholesterol and improve cardiovascular risk markers when they replace saturated fats. Think of saturated fat as making your blood saturated with cholesterol, and that leads to plaque buildup in the coronaries. The biology of dietary fat is nuanced with some confusing terminology, but it's been really well studied, and the pattern across data in humans is very consistent. Okay, we've learned about fats and oils, saturated and unsaturated fats, mono and polyunsaturated oils, and omega-3 and omega-6 fatty acids, with linoleic acid from omega-3 and linoleic acid from omega-6. What about seed oils? Well, seed oils are high in linoleic acid. What is it? I'm glad you asked. It's a normal, required dietary fat that plays a structural and metabolic role in human physiology, like we're about to cover. That's important to remember. Basically, linoleic acid as a stand-in for seed oils in the studies we review. And now we know from earlier that it's a polyunsaturated omega-6 fatty acid. Okay, so part 2, seed oils. Okay, we found our way via oils and omega-6 fatty acids to seed oils. Seed oils are edible fats extracted from the seeds of plants. They are primarily used for cooking, baking, food manufacturing, and as ingredients in packaged or processed foods. Which ones are seed oils? There are oils from soybean, corn, sunflower, safflower, canola, otherwise unfortunately named rapeseed, cottonseed oil, grapeseed, and rice bran. Those are different than fruit oils like olive oil and avocado oil, and they're different than animal fats like butter, ghee, tallow, or lard, as well as different from tropical oils like coconut oil or palm oil. So that's what they are. How are they made or manufactured? That is one point of controversy. To get the oils, first the seeds are harvested and cleaned. The oils are released by pressing and then, most controversially, by a process called solvent extraction. They are refined to remove impurities. That also removes odors and free fatty acids. Then they're filtered and stabilized. So in most all cases, they are definitely a processed food substance. Why do this? From a food engineering perspective, the processing makes them shelf-stable, neutral tasting, and inexpensive. So they get widely used in restaurants and food manufacturing as the oil component, or I would argue as a cheap filler. To interject, I have two biases to account for. One is in favor of being evidence-based. What's reality? Then another is a bias against processed foods. I recommend and mostly follow a varied diet of whole foods, limiting or being really selective about ultra-processed foods. So, while I recommend eating whole foods without ultra-processed ingredients, this video is about understanding whether or not this specific thing is bad, and for that, I need to be evidence-based. So back to chemistry. Chemically, these seed oils are made of unsaturated fatty acids, especially the polyunsaturated fats, which can be delightfully shortened to PUFAs, notably that linoleic acid that I keep mentioning. They have smaller amounts of saturated fat and monounsaturated fat, and they also contain some trace plant sterols, which will be a topic for another video. Importantly, they don't contain any cholesterol. So now, the seed oil controversy. These seed oils were introduced more widely in the 20th century as replacements for animal fats high in saturated fat, and basically to be used as a filler. And now people, seeing how disease burdens have changed over time, have become fixated on this one dietary element. They have concerns that the shift toward including seed oil in the diet parallels observed increases in chronic disease. But like my friend in college liked to say to try to sound smart, correlation doesn't mean causation, and the metabolic effects of omega-6 fats have been tested directly in controlled feeding trials. Let's discuss some of those right now. Now that we understand what oils are and what seed oils are, let's dive into a couple specific studies that cover key concerns about seed oils, and let's see if the reality matches the social media narrative. Topic 1. Do seed oils cause inflammation? Study 1. Johnson and Fritsch's meta-analysis from 2012. They addressed the concern, does dietary linoleic acid, remember that's the primary omega-6 fat in seed oils, does linoleic acid increase systemic inflammation in humans? Their methods, this was a meta-analysis of 15 randomized controlled feeding trials. Participants consumed diets with widely varying linoleic acid content, ranging from about 2% to over 20% of total caloric intake, for durations of between 4 weeks and 1 year. The inflammatory markers measured included CRP, IL-6, TNF-alpha, and soluble adhesion molecules. What were the results? Across studies, increasing linoleic acid intake did not increase systemic inflammatory markers. There was no dose-response relationship between omega-6 intake and inflammation. Several trials showed neutral or actually slightly lower CRP levels. What's the clinical takeaway? In controlled human settings, linoleic acid does not behave as a pro-inflammatory nutrient. The claim that omega-6 fats inherently drive inflammation is not supported by randomized human data. Study 2. Rhett's 2009 controlled feeding crossover trial. The clinical question: does replacing saturated fat with a seed oil increase inflammation or oxidative stress? The methods. Adults in the study consumed a diet in which approximately 10% of calories from saturated fat were replaced with safflower oil over a 10-week crossover period. Inflammatory cytokines, oxidative markers, and lipid profiles were measured. The results. LDL cholesterol decreased significantly, and there was no increase in inflammatory markers or lipid oxidation products. The clinical takeaway? Replacing saturated fat with a seed oil improves lipid risk markers without inducing inflammation or oxidative stress. Concern 2, oxidation. All right, study number 3, now addressing oxidation. Zhou and Min and their 2006 food chemistry review. The clinical question: under what conditions do polyunsaturated oils oxidize into harmful compounds? The methods. This review synthesized laboratory and culinary studies examining oxidation products formed during heating, storage, and repeated frying of vegetable oils. The results. They found that oxidation increases substantially with prolonged high-temperature exposure and repeated reuse, particularly in deep frying contexts. But, an important finding, they found single-use heating at home cooking temperatures produces relatively low levels of oxidation products, comparable to other fats. The clinical takeaway: oil oxidation is a function of how oils are used, not an intrinsic toxicity of seed oils. Repeated high heat reuse is the problem, not normal culinary use. Oxidation study number 2, study number 4 in our review. Wagner's 2021 experimental frying study. The clinical question: do seed oils produce unsafe oxidation products during prolonged frying? Their methods. Canola and sunflower oils were subjected to extended frying conditions. They measured polar compounds, aldehydes, and degradation products over time. The results: oxidation products increased with time, but remained within established reasonable food safety limits. No evidence suggested unique toxicity compared with other commonly used oils. The clinical takeaway: seed oils are chemically stable enough for normal cooking. Heating conditions matter more than the oil type. Concern 3: seed oils and cardiovascular outcomes. Okay, study 5. This is a fun one. The LA Veterans Administration trial from 1969. Clinical question: does replacing saturated fat with polyunsaturated seed oils reduce cardiovascular events? Methods: 846 men were randomized to a diet high in polyunsaturated fats like corn, soybean, safflower oils, or a standard diet. The trial ran for 5 years in a controlled institutional environment. Results: serum cholesterol fell by about 13%, and non-fatal myocardial infarctions were reduced by nearly 50%. The total mortality trended lower, but was limited as a finding due to competing non-cardiac deaths. Clinical takeaway: substituting saturated fat with seed oils is beneficial. It reduces coronary events in long-term randomized settings. Now you could ask, why include a study from 1969? Well, it was well done, it's relevant, and we've known this for decades. Study 6, the Minnesota Coronary Experiment, a reanalysis from 2016. The clinical question: does lowering cholesterol via seed oil substitution reduce mortality? The methods: over 9,000 institutionalized patients were randomized to replace saturated fats with corn oil, basically margarine. They analyzed mortality and autopsy data. Results: LDL cholesterol fell significantly. Though we should note, mortality differences were not statistically significant. That was largely due to advanced age and non-cardiac deaths. Impressively, autopsy data showed fewer atherosclerotic plaques with lower cholesterol. Clinical takeaway: LDL reduction occurred as expected. There were documented anti-atherosclerotic effects. Imagine if someone that was 30 fell prey to misinformation and lived for decades substituting animal fats and saturated fat. Study 7, the Mensink and Catan meta-analysis. Clinical question: how do different fats affect LDL cholesterol quantitatively? Methods: dozens of metabolic ward studies were pooled, comparing isocaloric fat substitutions. The results: replacing 1% of energy from saturated fat with polyunsaturated fat lowered LDL cholesterol by 1.8 mg per deciliter. Takeaway: seed oils reliably improve lipid profiles when used instead of saturated fats. All right, what a rush. What have we learned? Across controlled feeding trials, inflammation studies, oxidation experiments, and cardiovascular outcome trials, a consistent pattern emerges. Linoleic acid does not increase inflammation in humans. Seed oils lower LDL cholesterol. Cardiovascular event rates decrease when seed oils replace saturated fats. Oxidative harm appears under processing or repeated high heat abuse, but not in home cooking conditions, and it's more intrinsic to oil than it is any property specific to seed oils. So, much of the fear around seed oils, I've seen that it comes from people that haven't seen or treated a heart attack in real life. They don't have a biochemistry background like I do, a medical degree, or tens of thousands of hours working with patients. The people that spread misinformation seem to do it to create a concern that they can use to capture attention, build their own brand, and profit off of. But they're harming people by spreading a misunderstanding and promoting harmful health changes. Or best case, wasting time and wasting concern, better directed elsewhere. So based on the literature, seed oils are not toxic. They're biologically active fats that, when replacing saturated fats, improve lipid markers and reduce cardiovascular risk. The data do not support the claim that they are uniquely inflammatory or dangerous in typical dietary use. For me and my family, we mostly use olive oil, and we use butter or whatever oil if or when a recipe calls for it. But that's part of eating a balanced diet. And part of a life pursuing health, not conspiracies. If you have any questions about this video, please comment below. If you liked, please share it with a friend. And hitting subscribe helps me spread evidence-based messaging to others. As always, I wish you the best with your heart health. I'll see you next time.